we were talking about standard protocols, and we were talking about the fact that you can't really use the standard web stack for all IoT stuff. Don't get me wrong, if you have access to full mains power and limitless money to build your IoT device, there's absolutely no problem using all that standard stuff, but in general you won't. So we were talking about this. So we had covered the bottom one where we talked about 802.15.4, and now we're up to the internet layer. Okay, and we're going to have a little chat about 6LoWPAN just briefly. Don't need that. I'll come back. I don't want that. Okay, so that's where we're going. So what is this? We mentioned it last week. 6LoWPAN. It's a internet layer protocol, and the whole idea is you can scrunch IPv6 packets into a smaller space, right? And you get to use 802.15.4, which were, oops, come on away, these lads down here with this, but you still get all the benefits, or most of the benefits, from IPv6, right? So you got more access to IP address and all that type of jazz, right? So, and as I said, there was some good information. This was the slide we left it on last week. TI, because they make the chips. If you want to learn a little bit more, there's some stuff there. Okay, right. So a typical topology, and this is important, right? In other words, how does this stuff all fit together? So you might have some form of sensors or whatever here, okay? And you have what's called a 6LoWPAN router, right? So these are using 6LoWPAN, or they're using IO2.15.4, right? Which we said was the nice constrained one, okay? So that's radio links to here, and you might have two sets of that, right? A border router and a standard router. Okay, so these two are both 15.4, so they're both radio links, right? And there's something important about those radio links that we're going to talk about in a minute. So you can set this up, and then you're out to the big bad internet, and you can obviously get access then to send some up to the cloud or access other devices that might be accessible by the cloud. Okay, so that seems reasonable. Seems a reasonable topology. Another way of looking at it is this diagram. Exact same idea. You've got routers, okay, so in this case, this router is an edge router. These routers here are these lads here, okay? So you can spread it around that way, or you can have the PCs or devices or whatever straight in to the router, okay? So same idea. Oh, sorry, that's their standard ones, and this is that's just showing you that these can sit alongside standard PC and routers. But if you want to use 6LoWPAN, you need a specific edge router, and then in turn you build your network underneath that. Great, and it works, right? But there's a disadvantage. Can anybody think of what the disadvantage might be? Of course, if you read on in the slides, you know what it is, but can you think of what the disadvantage might be? Anybody? Okay, we'll get there. Right, so yeah, exactly, it's the range. So could I use this to put a low power GPS tracker on a bicycle, right? So think about it for a minute. I'd like to know, put one of these hidden in the saddle, and somebody nicks my bike, I'd like to know where it is. Well, unfortunately, you don't know where the bike's going to go. Would it be within range of one of these 6LoWPAN, or sorry, one of these routers, okay? Because remember, this stuff has limited range, 802.15.4, okay? So listen, it works fine, but there's an issue. So we need another solution whereby what you want to actually send a message to or from can be anywhere, right? It can be further away than 100 yards or 200 yards. And obviously, I know what you're going to say, we can use cellular, right? And that's fine, you can, but as we know, that comes with a price, all right? It'll cost you more. And so we need an alternative. And also something on a, what's the issue with if it's on a bike? What's one of the main issues if it's on a bike? One, yeah. What's the other one? Power, exactly. power. So do we really want to be charging this thing up all the time like we have to do with a phone? No. You know, we want to basically hide this thing in the saddle, bury the saddle, or maybe it's buried even in the bicycle somewhere, and we don't want to have to change it for years upon end, right? Ideally. And again, if you have something that sells really low, you could, yeah. But again, you're talking about a little bit more complication, a little bit more. You have to have, you have to buy a power converter. Okay, so there's all different things. I know modern bikes, Jesus, the batteries out, the Yazoo, and all that sort of stuff. But in general, we need some technology whereby we can have sensors remotely, and we can either send messages to them or get messages from them. They need to be low power and they need to be cheap, right? That's the whole point about IoT that I'm trying to drum into you. So we need another solution, right? Because the problem is short distance. So we need a solution whereby it cannot use low power Wi-Fi or Bluetooth, commuter routing point, that would turn commuter. We need a what's called long range solutions, LP-WAN, right? And if you have a look at that link there, it's a reasonably good article. And also this thing that I asked you to see, this here, this mandatory read, you need to read that, okay? If it says mandatory read, it means if you read it and understand it, it usually will help you answer questions in the exam, okay? So make sure you have a read, because it'll mention some of the things that we're going to talk about here. So has anybody ever heard of any of these LP-WAN? Most likely not. There's actually three at this stage, actually, because I talk about three now, but I forgot to update this land. There's three, and there's Sigfox, there's LoRaWAN, and there's one more. Has anybody ever heard of NB-IoT, narrowband IoT? Anybody ever heard of that? So it's another one, and what it does is it makes use of bandwidth that's on the spectrum. It's spectrum that's part of the cellular stuff, right? That's not being used. So in other words, if you have a cellular link, then you can take advantage of NB-IoT. All right. So we were talking about LP-WAN, right? And the topology. So as you can see, look, the topology looks, well, doesn't look too dissimilar than that, does it? But it is. There's one big difference, and that is that these base stations, which again, this will use radio, right? It's always radio for the last bit. But this link here is a much longer, we're talking kilometers here, all right? Multiples of kilometers here between this and this. So it's a bit like cellular, okay? And there's two different ones, well, there's three, but there's LoRa, there's Sigfox, and there's NB-IoT. And we're going to talk about all three at some stage, but just to introduce them here. And this is the topology. So again, we have our sensors. You have some form of gateways. For instance, Tala have a LoRa gateway on the top of the building. There are Sigfox ones dotted all over the country. And essentially, you set your sensors up. You can talk to this gateway, and then the gateway, in turn, talks to a server, and that's a standard IP link, right? Because again, typically the gateway is sitting on top of a building, which means it's got access to power, it's got access to normal LAN stuff or WAN stuff, okay? And you're into a server. Once you're into a server, you can do what you want with it. All right, so this is the cloud, blah, blah, blah. So big difference is this link here. These links are much longer than the other ones, all right? The previous ones, the 802.15.4. All right, that's the big difference. That's why they call it low power WAN, low power wide area network. Okay, so say we're going to compare those two later on. We're going to have a close look at those as regards how they work and security, and we'll also have a look at NB-IoT. All right. So that was a little quick look into the internet layer. All right. A look at six low pan, and basically then introducing the LoRa and the Sigfox. So if we go up another layer, we find, remember, this is all about a comparison with a standard web stack with stuff you might have to change for IoT. So standard web stack, we have TCP, UDP. We have TLS here, over here. See that there? That's the wonderful thing we did in second year. And we have over here, we have UDP and we have DTLS. So DTLS seems to be on a slightly different, DTLS over here seems to be at the same level as TCP. So let's have a chat about that. So before we do that, we have to just recall, and you guys are all experts at this stage, 4 years later or 3 years later, UDP versus TCP, and this actually plays a very, very important role in IoT. Anyway, you want to tell me why UDP is important versus TCP in IoT? Want to have a guess? Speed, yeah. Why is it? Which is quicker? Why is UDP quicker? Size of packet, UDP. But why is it faster? No handshake, correct? It's sort of fire and forget, isn't it? So if you think about it, less data on the line requires less power and it's quicker. But what's UDP's disadvantage? What's its main disadvantage? Yeah, you can't be guaranteed the stuff gets there. All right. So I think you know exactly where we're going with this. UDP sounds like it's a pretty good option for IoT because less data, quicker, means better for low power and cost, right? However, there is an issue, and we have to consider that because the minute we get into trying to secure that, right, we are going to have some issues here. So I'm not going to read that. You can read that. That's just the analogy. Again, I don't know when I'm going to read all this because, yeah, you can read that yourselves, right? It's really straightforward stuff. It's just comparing UDP. You know it off by heart at this stage. There's the summary, okay? So UDP is reliable versus TCP unreliable. So UDP is unreliable, TCP is reliable. All that means is the packets are guaranteed to get there with TCP. UDP, they're not. They're sort of fire and forget. The reason why, one of the reasons they're guaranteed to get there is connection orientated with TCP. In other words, you make a connection and everything is acknowledged, okay? Whereas UDP, it's not, it's just lashed out there. Just TCP retransmit if there's an issue, and no retransmission or windowing. You don't need windowing if you obviously don't have acknowledgements, right? Windowing is basically just, I presume you did windowing, yeah? You understand windowing? Blank, no. Interesting. Okay, so let me try to explain windowing. So we all agree if you use UDP and you're lashing stuff out there, right, you can take up the whole bandwidth and just, yeah, something like that, yeah. So just think of UDP for a moment. You're throwing out the stuff, there's no acknowledgement, so you can just lash the stuff down the pipe, agreed? And that's one of the great reasons why UDP is used for videos, right, broadcasting video. So the problem, if you didn't have the concept of windowing, with TCP/IP, because you have to acknowledge the packets, right? So think about it for a minute. If I send a packet and then I have to wait for an acknowledgement before I send the next packet, all right? So that's going to look like, you know, it's going to look pretty slow. If you were to look at it on a, let me just see something here. I'll just show you something here. Let's just open up this for a minute. So imagine I have my packet, right? Is this, and my acknowledgement was this, right? And so that's my packet, and that's my acknowledgement, okay? And then I would so let's just make it really simple for a minute. So it looks something like that, right? So pretend they're all the same length for the moment, yeah? So the yellow is the packet being transmitted, the green is the acknowledgement, right? So in other words, I can't send any more data until I get the acknowledgement, right? Without windowing, that's what it would look like, right? What windowing allows you to do is to keep sending while you have a certain amount, an agreed amount of acknowledgements outstanding, all right? So in other words, say our window was 3, all right? I could do, so instead of that, I would end up with, now we're going to do this, yeah, I'll show you this way. So I could literally do, I'm allowed 3 outstanding, right? So I could lash out the 3. The first acknowledgement would probably come in here, agreed? It's fine. I just keep going. The second one would probably come in here. The third one would come in here. But I think you can probably see that I can continuously send, as long as the acknowledgements are coming in some shape or form, I end up using up all the bandwidth so I can send. And there's no, see these little gaps here? I'm losing bandwidth here if I don't window. And that's how windowing works. If you try to do a download and you turn windowing off, it'll be a lot longer to do the download than it will be of any sort of file or data than if you have windowing on. It'll be so much quicker. So hopefully you understand that very crude example, right? You can look it up as well and explain it a lot better than me, but that's my very simple explanation, right? Sequencing, TCP, I could send the stuff. We all know that the IP networks out there, they can route stuff around the place. Don't all have to go the same place. They could, they could go in a different order. And the other end is guaranteed to put them all back together in the right order before they get handed up to the next layer in the ISO stack. Okay. Whereas UDP, good luck, just lashed out, and there's no acknowledgement in UDP there is. So that's a summary of TCP versus UDP, right? So you can see probably why UDP is advantageous to IoT, right? Quicker, cheaper, less power. So there we go. There's the main disadvantage, UDP, blah, 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 blah. Exactly. Much better for multicast, which is one-to-many receivers, which is exactly what streaming is. All right, streaming video or whatever. Okay. There's some examples of UDP. UDP, anything where you don't care too much, you always get the data. You get away. Why do you get away with UDP be used for streaming data? Why do you get away with that? I probably told you this before, but why do you get away with it? Why do you get away with the fact that some packet might arrive in the wrong order or one might get lost? Why do you get away with that with video? Within reason. Obviously, if a lot get lost, you're going to see something on the screen looking dodgy, but why do they get away with it normally? No, it's not because it's buffered. No, that helps, but it might get lost altogether. No buffering is going to help you if it gets lost. Why do you get away with it? How many frames per second typically is video? Exactly, yeah. 60, grand. Do you reckon your human eye can detect if 2 or 3 get lost or 1 gets lost? No. Do you know how many frames a second the human eye can sample? It's typically about 25, all right? That's well, sorry, you can obviously sample those, but you won't notice anything going wrong unless you're being shown something that's less than 20 frames per second. So in other words, if I showed you a video at 20 frames per second, it would look shit. If I show you at 25, it's fine. 30, fine. You won't notice much difference between 30 and 60. It's just slightly better quality. All right. So that's why UDP, you get away with it for video. All right. TCP, any games, for instance. And so there's a few examples there, right? So TCP, anything that's reliable, security things like SSH, it has to get there, right? It has to be reliable, so you have to use TCP over IP. That's the detail. I'm not going to read that. You know it off by heart if you don't read it yourself. And there's the detail on UDP. Again, very straightforward. You've probably done it 50 million times. You do need to know it, so you need to know it. I'm not going to read it. So this is the important part. We've established that UDP would appear to be better for our typically IoT use case, right? Sensor reading, in other words, if you're reading temperatures and it's sending them every 5 minutes, does it really matter if one goes missing? Well, it might matter if it was for a fire alarm and you were only reading, say, once every 5 minutes and the bloody smoke detector detected it, and it was 5 minutes later before you set the sprinkler off. So you do have to be, so in other words, if you were doing a smoke detector sensor, you shouldn't really be sending one reading every 5 minutes if you're using UDP. Otherwise you might have a problem. Okay, sprinkler might be delayed by 5 minutes. Does anybody understand what latency means? Did you ever hear that word, latency? Yeah, essentially, Luke's right there. It's speed of communication. But specifically, what I would mean there is there's a latency problem if we had a smoke detector, right, only sending every 5 minutes. That's bad. That's a really high latency there. Okay, in other words, there's a delay. There's a possible delay. Yeah, whereas we couldn't afford to do that. All right, so we can't. Again, latency will be important. We'll talk about it later, but just it is an important term in terms of when you're deciding what protocol you're going to use for your network. Latency is an issue. Can I afford high latency here? All right. Low latency means everything is really quick. So in other words, I would design a smoke detector sprinkler system with a low latency. In other words, reading every whatever X seconds, because I need to know I can't afford not to turn that sprinkler on, right? And security for UDP. Now there's a whole separate discussion, and we're going to get into it big time. But how do you build security on top of UDP? Because, well, how did we typically beforehand in second year, if I asked you, how do you want to have a secure link? What's the one you'd quote? Can you remember one we did ad nauseum in second? Because you look at the next slide, you probably know. But what's a relevant one? Do you remember this? Do you remember our friend? Remember this? TLS. Drove you mad teaching you that in second year, and you can't even remember it. Oh dear. Anyway, TLS is the obvious one. And as I said to you, if you ever need to secure a link, don't go reinventing the wheel. Mind you, I might ask you to do that in the CA, but that's a different discussion. TLS, the obvious one, if you want to encrypt or secure a link. But it has an issue. Anybody know what the issue is? There's a clue in the title. Guess what TLS needs in order to work? Now, if it was UDP, we'd be grand. What does it need in order to work? What does TLS assume? It assumes it has TCP underneath it. In other words, it assumes, yes, reliability, Connor, the stuff is going to get there. Nothing is going to get lost. So if I run TLS over UDP, not a good plan. Okay, so I have a problem here. I would like to, why do I want to use TLS? I said to you, why don't you just build your own? Why use TLS? Why would I use TLS? Remember back to what you learned last week in this. What's the reason why I want to use TLS? It's a standard. Very well. Very good, Dylan and Sean and Connor. Jeez, you're all at it. Always, always, always we want to use a standard. So we would like to use TLS if we have to secure a link. Right? Why? Because lots of things support TLS. If we home grow something, guess what? Not everything will support it. Unless you're Apple. Then you home grow whatever you want. And then you charge everybody a fortune to use it, right? But that's a different argument. So that was our TLS, remember? Our wonderful TLS whereby, the client, and what was the example we had for TLS? It was the browser and the web. Simple one, right? The client is the browser. It says hello, it gets back the public key, it checks it with its, that it's certified public key, and then it, exchanges a random number, and the random number becomes the symmetric key for encrypting. Yeah, cool. Lovely, easy. The problem is it uses TCP/IP, and we want to use UDP because UDP is lightweight, speed, cheaper, turns on radio for longer, all that sort of jazz. So we have a little bit of an issue here. So we need something different. And guess what? There's a thing called DTLS. Isn't that nice of them? It's, I'd say relatively recent compared to the age of some of this stuff, right? So DTLS is an implementation over TLS over UDP, okay? So TLS uses TCP, TLS uses UDP. So it's really important that you don't get these confused because they're totally different. Well, they're not totally different. You still get all the TLS features, but the underlying layer is totally different. One is TCP over IP, the other is UDP over IP. Okay, so UDP comms exists, as we know, blah, blah. So how do we fix it? We've just said that we want to use TLS, but TLS requires reliable comms. So if we're going to use DTLS, we're not going to change UDP. UDP is UDP. You can't just change the standard. So we're going to have to implement something in the DTLS. Well, we're not going to have to. Someone else did it. DTLS must implement stuff that TCP gave us. All right, and that's exactly what it does. DTLS is similar. It solves the two main problems, right? It implements packet retransmission, sequence numbers, and replay detection. Everybody know what replay detection is? Know what that is? It's up to hackers. It's up to man in the middle. It's basically somebody replaying. There it is. There, it's an attack on a security using a replay of a message from a different context. So in other words, you record using Wireshark and an old session, and you try and replay that, jump in the middle, replay it, so and fool the two ends into thinking that it has a good connection. All right, that's all of it. That's basically all it is. So the whole point is DTLS is, because it's using UDP, it has to implement some of the stuff that TLS does, that TCP does for TLS. Okay, so it does all those nice features. So DTLS does these, but it also implements the bits that are missing for UDP so that you get reliable comms. All right, and that's all that's saying. It's doing the retransmission, sequence number. They're the two biggies. The replay is an extra bonus. All right, we get into it a little bit more detail later on. So we'll do that, more on that later. Okay, so we've introduced, the main thing we've introduced here is we've gone and looked at this, and we're now up as far as here. Okay, and basically we've shown that on the IoT side of the house, we want to use UDP, and the minute we do that, we're going to have to use DTLS, whereas over on this side of the house with a standard web stack, we would normally use TCP and we would use TLS if we wanted security. All right, so that's that one. Let's have a look at numero 3. How we do it on half, right? We should have a look at this one. So part 3. Okay, so typical what we see in the application layer, right? What do we see? Well, on the web stack we see HTTP, DHCP, that type of stuff, right? Big one being HTTP. Over here, we've got other ones, right? There's our friend MQTT, and there's another friend we're going to become familiar with is CoAP. And CoAP is a bit like HTTP, right? MQTT we know isn't a bit like this. It's different. It's a publisher-subscriber model. So we're going to talk a little bit about MQTT. Well, we know it from the lab at this stage, but we're just going to briefly go through the theory behind it again, and then we'll talk about CoAP. All right? So let's get into it. So MQTT, I'm going to go through this reasonably quick because I'd say you know it ad nauseum at this stage. As we know from our lab, the whole point is you censor whatever, publish status to a broker, and the broker then sends that out to anybody who has subscribed to get that message. Now, one of the things I'm toying with at the minute is what to give you for your CA1. And I'll be honest with you, it's going to depend on how many of you there are. Usually I give an implementation that I want you to solve in MQTT. But I'll be honest with you, it takes a lot of correction if there's 30 something of you. So I'm waiting to see how many, the number I finally have before I decide whether I go MQTT, whether I go CoAP, or whether it's a design thing as well as an implementation, or it's a design thing plus a prototype. But we'll wait and see. But you can use MQTT broker for nearly anything, all right? Because the beauty of it is you can use it point to point, or you can use it point to multi-point, right? It has significant advantages. So anyway, we know it at this stage, right? So this is just run through in case anybody was asleep, the order, which is important, right? So you have to subscribe first. In other words, you have to be interested in something, yeah? So in this case, we're interested in temperature. This fellow over here is going to publish the actual temperature, maybe every minute, 10 seconds, 5 minutes, once an hour, don't care. Publish it to the broker, and then anybody who's subscribed gets the values, all right? The single most important thing here is the guys at the either end don't need to know the IP address of each other, and that is the major advantage, right? The only person whose IP address you need to know is one broker, all right? One. And I mentioned there's I think on the, and again, from, I haven't made it visible yet. I think you might remember from second year, people who did the project in second year with me. There's public MQT brokers out there called, if you look up Hive, right? Let's have a look here. So if you go here, here we go. So there's actually a public broker, right? And so in other words, you can, from this environment, the Google Cloud, you can basically mosquito and use the public broker. You don't even need to run the broker locally on the Google console environment. You can use someone else's public broker, and off you go. It's really, really powerful. All right. So that's the basic architecture. Very, very simple. But as I say, I could get you to build lots of different things, and I'm toying with how far I'll go with it. Okay. So there's the architecture. It's client server. Every sensor is a client, and it connects to the broker, who's the server. Okay. It's totally different than other ones we will meet. For example, CoAP, right? In the CoAP design, which we will come across, the sensor is actually the server, and you are connecting to the sensor as a client, and you are using HTTP, like puts, gets, all that type of stuff, to get information from the sensor or put information to the sensor, okay? Or the whatever it is, okay? Sprinkler thing, doesn't matter, right? So there's a fundamental difference here. In MQTT, the endpoints are clients and the broker is the server. In CoAP, which we will come to, the sensor is typically the server, and if you want to talk to it, you're obviously the client, right? It's message orientated. Every message is a discrete chunk of data, opaque to the broker. In other words, opaque means the broker doesn't care about the message, right? Sometimes it's encrypted. So broker is just routing. Very powerful, but that's all it's doing. Every message, as we know, is published to a topic. They can be very, very simple topics, or they can be a hierarchy of topics. Clients may subscribe to multiple topics. And we'll do this in the lab. Every client subscriber receives every message public to the top. Let's say we've done simple stuff so far. We will do more complicated stuff as we move through. So in other words, imagine a simple network with 3 clients and a central broker, blah, blah. 3 clients open, subscribe to topics. We've done this. It's pretty straightforward, okay? There are serious advantages to using it. You've seen already how easy it is to set it up just with basic container with Google, but you can, anything that's using a Linux environment, be it a Raspberry Pi or whatever, you can set it up to use Mosquito, piece of cake, just download the right packages. Those clients, you install 2 packages, Mosquito and Mosquito clients. Those Mosquito clients are really, really lightweight. Yeah, that's what this means. In other words, they're small executables. They don't need a lot of stuff to run. Minimal packet overhead. There's little or no packet overhead. It excels transferring data order in comparison to major protocols like HTTP. Major advantage. Why? Because the radio is on for less. Blah blah blah. as I say, that third one is really which means that you can have an MQTT client on a very simple device because you don't need much processing power. Okay, ease of use was a major concern, development of MQTT. And constrained devices. Does everybody understand what a constrained device means? Do you know what a constrained device is? Well, it says it there. Limited resources today. Might be a low power processor, or it could be not a lot of memory. Okay, they're the typical two constraints you have with an IoT device. I don't have 50 million gig of DRAM. I don't have a massive hard disk, and I have a shit little processor. Right? That's typically what a constrained device means. And this point is key. Every protocol that I know can do one-to-one. Some can do one-to-many. Not many can do many-to-one, forgive the pun. All right? So it's extremely powerful. What governs that last point is who subscribes. All right? So in other words, you could build a messaging system that was just one-to-one and the broker decided who got it based on who subscribed, right? Or you could build a broadcast system one-to-many, or you can build a concentrator system whereby there's lots of sensors from many different places and they're all coming into one server. Extremely powerful and very, very simple. So we've done this. I'm not going to do this. Topics. Okay. So topics I think we touched on in the lab. We will be doing them a little bit more in subsequent labs. All right. I think that I gave you a little example of it last week, but it could be, I think the example I gave you was, something in, where was it? Different countries and houses and rooms or something, wasn't it? Doesn't matter. It can be anything, right? The main point is you can have a hierarchy. It's like a file system, right? And you can have a hierarchy, and you can subscribe to these. You can subscribe to that. I could subscribe to that exact topic, which means I would only get the temperature in the living room, right? Or as we know, we can use wildcards. I'm going to go back to wildcards. Where's wildcards gone? Oh, I didn't cover wildcards. I cover wildcards in the lab, not here. We know from wildcards, right? I can put in a hash sign, and it means everything underneath here. Or I can put a plus sign. So in other words, if I put a plus instead of living room, it would give me the temperature for all rooms on the ground floor. Okay. If I put a hash in there for living room, it would give me there might be temperature, there could be humidity, like we did, right? So it's sort of similar. But anyway, we'll come back and we will learn more about those in the labs. But it's very straightforward. But you just need to do a few examples and then you get your head. It's so simple, it's embarrassing, but extremely powerful. There are some. Anybody know what QoS means? It's an important term you need to know when you're comparing two protocols. Everybody know what it means? You ever heard it before? Quality of service, exactly, Paul. And really what that means is a guarantee that the damn thing worked. So we got this 3, fire and forget, which means not sure, might have got there, might not. Okay, so you can set up the MQTT protocol to be just lash it out there. You can also set it up to be make sure it gets there at least once. So in other words, it could get there more than once, right? And that if you need to be careful how you design your system, because if you design it and you assume it's only going to get there once and it arrives there twice, if that was a counter, you could have a problem, right? So, and then the last one might be what you want. If it needs to be really, really accurate, like a counter, you're counting stuff that's coming in, delivered exactly once is what you want. Or in other words, if you used MQTT to build up I'll be honest, you could use MQTT to build a WhatsApp type messaging, right? And if that's the case, you would definitely like the last one, right? You don't really want the message getting there twice, and you don't want the case where it never got there at all, right? So if you built a messaging system using MQTT between multiple people, you would most likely use QoS of the last one, all right? But if you built it to use up a temperature sensor thing that you were sending temperatures every 10 seconds, you'd most likely use fire and forget, all right? Because you know that they're going to get there eventually. You get the idea. Security. So brokers require username and password authentication to TCP will be encrypted with that. There you go. All right. So MQTT is using TCP, and which means we can use TLS. That seems like a little bit of a contradiction, doesn't it? We wanted MQTT because it's nice and simple, and now I'm telling you that the default is it uses TCP, so I can use TLS. You're probably going to go, Pierce, that's a lot of shite. But it's not, because the MQTT is so lightweight. Otherwise, the first version of it used TCP, so it could use TLS. But guess what? There's other versions whereby it uses UDP. We'll talk about that later. All right. And here it is. Here's part of what we're going to talk about, right? It's designed to be lightweight. It has drawbacks. You have to support TCP, and as we've said, that can be an issue. MQTT topic names are often long strings. So we've seen that, yeah? We've seen things like, that's a long string, right? Which means that could be a lot of data. How are you going to reconcile that with protocols that you're trying to squash stuff into tiny packets, like we talked about with that 802.15.4, remember? Okay, so these long strings could cause a problem, and TCP could cause a problem. So that's why they came up with another version of MQTT called MQTT-SN, right? And it addresses the two issues: the UDP mapping of MQTT and adds broker support for indexing topics names. What do you reckon that is? Okay, UDP, we know what that is, fair enough. So there is a version of MQTT you can use at UDP. So obviously somewhere in there, MQTT, that version handles the retransmission, right? However, or might use DTLS if it's using TLS. Adds broker support for indexing topic names. What do you reckon that means? Any idea what that means? Because I deliberately didn't explain it, because I'm sure you can go look it up, but what does it mean? Maybe any idea? Indexing topic names. No, not formatting. If you index something, what does it typically mean? It means that item number, this item is number 51, that item is number 52. So all it means is, if you're, rather than, remember, if you're publishing or subscribing, so you only subscribe once. If you're publishing to a topic and you're doing it every 10 seconds, right? So say, for instance, I'm publishing to that every 10 seconds, right? It means I'm sending a publish message with that big long string of misery, right? Every 10 seconds. That's a bit overkill. I'm sending a temperature, which is a value, which is 1 byte. But in order to send it, I have to send this big long strong of misery, which is about 30 bytes, right? Which, that's a bit stupid. So what it allows you to do is it allows you to go, that big long string of misery, I'm going to tell the broker that that corresponds to topic number 57, right? Which means if I publish to topic number 57, the broker knows anybody who has subscribed to that big long string of misery, which is ID index number 57, I'm going to send them a message, right? So all it is mapping of a simple index or a number to a particular topic. Okay, that's what that means. Cool. RESTful APIs. Anybody remember what these are? Do you remember doing bits and bobs on these? I know you're not programmers, but you will have come across this over the years. RESTful API. There's a reason why we are going to reintroduce these. Unfortunately, yes. Why unfortunately, Kieran? Unfortunately. Why unfortunately? Oh, head wrecking. All right. Well, the good news is I'm not going to make them head wrecking for you. Okay. I'm just going to remind you that they exist and what you typically might use them for. And the reason why, is Remember I said we've MQTT, and I said there's another very popular protocol called CoAP, right? And CoAP is very, very similar to HTTP and uses RESTful APIs, which has obvious advantages when, again, you're building on standards, right? So that's why we want to just a little reminder of RESTful APIs before we go any further. And this is the last thing we do today. So it isn't that head wrecking, right? So a very, very simple example, okay? So imagine you have, in this case, it's movies, right? Probably not the best. I should change this example to be something to do with like a sensor, all right? But anyway, this would be a get. If I want information about movies, I send a get API to the server and it gives me back the response with, these are all the movies, for instance, that are showing this week, right? If I go get movies and I pass in an ID, that ID might be a specific movie. I would get information on that specific movie, not all the movies, okay? And then what's the difference between post and put? Can anybody remember that? Can I remember the difference between post and put? Yes, exactly. Right. Post creates a new. Geez, you see, you do know it. You haven't forgotten it, right? Yeah. So post would be to put information up there for a new movie. Put would be to update the information that's already there. Very good. Or one or the, I can't remember which it is. Anyway, it's one or the other. And then delete obviously blows it away. So imagine if you had a sensor which acts as a RESTful API server, and you wanted to say, if it's a smoke detector, you're just doing a get of, give me the value of the smoke. Is it on or is it off? Or is it, if it's something that's reading temperature, you would say, get me the value of the temperature, yeah, of the sensor, and you get back the different temperature, right? If it's to turn on a sprinkler, you'd probably be doing a put or a post, all right, to turn on a sprinkler. You get the idea. The sensor, the sprinkler or the smoke detector is the server, and you who want to control it are the client, and you're using RESTful APIs to control it, okay? That's all it is. Hopefully you get the idea. There you go. All right. There's the answers. You probably just read the next page if you're clever, okay? So I'm not going to do CoAP today. I'm going to do CoAP the next day, right? So all I want you to remember is CoAP. There are two major protocols at this level. Let me go back. Okay. These are the ones. See, you can read about these if you want to knock yourself out, right? I'm not going to cover those. There's multiple ones exist. These are the two dominant ones. Okay. So I say we're going to continue to use MQTT in the lab. We'll most likely have a play with CoAP as well. The CA may be one or the other. I'm still deciding based on numbers, because otherwise, if I get it wrong, I'll spend about a month trying to correct the shagging things, and so I ain't doing that. So what I want you to know at the end of all this is the difference between these two. And as I said, the big difference is publish subscriber over here, and CoAP is client server using RESTful APIs. Okay, and there are advantages to that, which you can probably see coming, which is you can treat it nearly like it's very similar to